Yes, so today we are going to learn about the thermochemistry and kinetics. So thermochemistry, that is related to thermal or heat, right? Thermal and okay. So this is thermochemistry, and then due to this thermal or with the heat changes, how the reaction rate increases. The reaction rate, how the reaction rate increases or decreases or whatever. Yeah. So this is the thermochemistry, and for us today, the learning objective, we'll learn to know that how do we describe the changes of energy, okay, during the energy profile. What do we mean by energy profile is how the energy of the total system. What does the system means? Where in the environment a reaction is occurring, A plus B, a reaction is occurring. Yeah, please come in. Okay. So A plus B is the reaction is occurring in here. So I mean environment or the energy is changing for this environment or for the system. So how the energy is changing with the time of the reaction is proceeding, right? The reaction proceeding towards completion. So at the 0th time, there is no reaction, and then the first minute, second minute, third minute, fourth minute, and then final minute. So how the energy is changing according to the progress of the reaction. And we will express it with the del H, that is the enthalpy. Call it enthalpy, the changes in heat of the reaction. And later on, we will show that how collision theory helps to get us to understand that how the reaction rate actually, goes faster, slower, or how the collision happens between the particles helps the reaction to occur. All right. And also the concentration, the particle size, the temperature, and the pressure, and also the catalyst, right? The catalyst we add, how does it help or increases the reaction rate? So now energy and chemical reactions. Chemical reaction, of course, because there are different type of atoms there and there is a collision happening between them. So when there is collision happening between them, right, there is a possibility that they can form the bond, break first and form a more stable bond which has a lower energy. So they do not have to be always excited. And that is how actually that the reaction occurs, because of that formation of new type of bonds which has a new compound, new product which has lower energy. So they are not very excited, and then they don't always go and fight with others, right? They are stable, they want to stay stable somewhere undisturbed. So that is why the reaction occurs. And this is expressed as the difference in enthalpy from the product and the reactant, the difference between this product and the reactant. All right. So if the product is lower energy than the reactant, it is negative. And if it is otherwise, it's positive. When the enthalpy is negative, if it is negative in this way, we call it exothermic. We'll show it exothermic, and this is spontaneous reaction. The reaction will occur more easily in that case. So what actually does it mean that the negative and positive number or positive what do you call it, negative and positive of enthalpy. So if we do the energy diagram, like here the energy on this y-axis, we are putting the energy here. It is, let's say here we started 0. Of course, when the reactant is there, reactant was always, to some extent, they were stable. So we consider it as 0 where they started. And then no, naturally, this is negative side, which is going down, negative, 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 and which going up is positive. So this is positive side, this is negative side. So when the reactants is going, the product is formed from the reactant, and this is going to negative side. The energy barrier energy is going to the negative side, right? Because the energy reduces for the product than the reactant. So this, how does the energy reduces or become less? Because of this reaction, they release emit the energy. How do they emit the energy? As a heat. The energy is released as a heat. Heat will come out from the system, or this is, let's say the reaction is occurring inside, so heat is coming out from this all these things. The heat is coming out from all these things, and that is how the product become less energetic or less energy. The opposite thing can occur when the reactants is in the less energy, but the product that is formed is higher energy. All right, the product is becoming getting more energy, more how do you call it, more excited product. The product is having more energy in them because they have absorbed more energy from the environment. How do they absorb energy? Also as a form of heat. They take because our temperature is, let's say our room temperature is what do you call it, 28 degrees now, 27 degrees now, right? But if I put two reactants together, they will become cold, so they will get more energy. So they are actually like 10 degrees when I mix together, and they are getting the energy from the environment and becoming warmer. So that is why some of the solution, especially if you dissolve some salt in the water, you'll see that the water temperature is a bit cold because it is taking energy from the environment, because it is less temperature. It has less temperature than the ambient temperature. So this is exothermic. These two terms we will be using frequently afterwards are quite troublesome sometimes for those who do not pay attention, and these two terms will be important for us to know, because many of the questions are actually does not describe what is exo, what is endo. It will just tell that it is exothermic, it is endothermic. So we have to understand what is the exo. Exo means when it is exiting heat, right? Exo means explosive type, that means giving a heat. And the opposite is endo. Doesn't matter what is opposite, but just opposite is endo. Just remember in that way. Okay, exo means it is giving heat, like yeah, explosive, or you do burn the gas, right? At your stove, you turn on, and then the gas start to burn your cooker, and you get energy from it. So this is an exothermic reaction is occurring. We will see that in later slides. Okay, so now there is one question here actually. Which statements are correct for the all exothermic reaction? First, the enthalpy of the product is less than the enthalpy of the reactant. And we have seen this is correct. because here it is, the enthalpy, that means del H is negative, right? Del H is negative, but del H is positive for endothermic. The del H is negative for exo, and this is true. The reaction is rapid at room temperature. It doesn't, I mean, there is no rule in that way that if the room temperature it will be faster or high temperature it will be faster. It's not true. So A is correct for this. The thermochemical reactions, that or the equation actually, what is the usage of these thermochemical equations? One very simple example is that magnesium, this is one metal, just lithium, magnesium, sodium in that first column of this periodic table, you will see that. Sorry, it is in the second column of, yeah, it's the second column, that means that is a group 2 element, this magnesium, and like others as well, sodium, lithium, they react very vigorously, so we cannot use that one. And then also the product they produce with the mix of water, sodium, lithium, potassium, and that is also not very safe for us. But magnesium oxide or hydroxide is relatively safe for it to be used for meal ready to eat or something like that, or for camping purposes or for the military services that is be used, right? So what they do is just need to put some water inside this. There is magnesium inside, and then this magnesium will react with this water and rigorously, and then produce a lot of heat. That is negative 353. That means quite much heat. It is quite much. This heat will be produced by adding water to this magnesium, and the food will be just nice and cooked again, that's like a ready meat or ready meal, like that. So this is one example of it. And what is happening is magnesium is reacting with water, 2 moles of water, right? The reaction stoichiometry of this reaction is 1 mole of magnesium reacting with 2 moles of water, producing magnesium oxide and hydrogen gas, and 1 mole of hydrogen gas. So that is good thing that not much, that the hydrogen gas is not that much, not that many or much. Yeah, hydrogen gas has been produced. So this is the energy profile. If we look at on the y-axis, we put some energy, we tabulate or we note energy, and x-axis, we show the reaction progress, right? Reaction progress, that means 1 minute, maybe 2 minutes, 3 minutes, 5 minutes, in that way, that how the reaction is progressing, or reaction is 5%, 10%, completed, 20% completed. In that way, we looking at the progress of the reaction. So now we started here the magnesium, and then we put water. When they did not mix, let's say that we did not add them together, but they were side by side. We did not add them together, just did not mix together, but they're just keeping side by side. What is happening is still they have the same energy. They did not do anything, no changes in the energy, right? Side by side. So this energy, right, here we consider 0 because it started at 0. 0 means it's stable. That magnesium and water side by side, they're just nice, okay, friends, good, no problem, no nothing. So we consider 0 energy there. And then as soon as we started, we mixed together, they become hot, like that. And then the energy, hot means what? The energy, right? It's There's so much energy in it. That means that is why they are hot. So this energy increases very fast. Very fast the energy increases. And then at some point it reaches to the culmination point. That means they reach to the maximum peak and then they started to cool down slowly. What is happening actually here is when they mix together, they start to collide each other. They start to fight. And then the magnesium and water, whatever bonds they had to break, they break. At this position, they had a lot of fighting until this point. And then they saw the opportunity that, okay, no need to fight each other. We have opportunity to break some, make some bonds here. And then they started to find started to make those bonds together, right? Started to make those bonds together. Once they started to make the bonds together, things become much easier, and then they release the energy once they made the bond, because they are now much stable and they're happy. They want to stay there in that way. Happier, they stay together, and then the bonds are made. Magnesium oxide and hydrogen did not make any bond. Hydrogen stay alone. It's okay, I'm staying fine, no problem. So this is how the energy enthalpy actually reduces then the initial state. So this is the changes in enthalpy, and this is the negative enthalpy, which is del H. But from where we started, the same level, we started 0 level. So from here until the maximum peak it reached, this is EA. This is the activation energy. This is the activation energy, right? This is the energy it has to cross to form the bonding. It must cross to form this bonding. That's the activation energy. Or we have to provide, if there is not enough energy in the system, we have to provide this much energy to the system or to the reaction to overcome it. Some of the reactant like this, and we started from here, right? We started from here, they go and then stay like this. A plus B, A plus B, we mix together. There you see that waiting, long time, no reaction occurring. Why? What's wrong? I'm not doing anything wrong. Why no reaction is occurring? Because it has not reached to this activation point. So what we do is we put some energy to it, to this type of reaction. I'm talking about the thing that I'm drawing, right, on the right side. So we put some energy, it means we heat it up, or we pressurize them. So what will happen is it goes until this point. Until this point, we heat this up or put some pressure or add some more concentrated solution. Once they reach to this point, okay, now they are good. They start to do the reaction, and then they can go to there or they can go to here as well. Endothermic or exothermic, depends. But once you have to cross this barrier. So this is the activation energy. Another problem here shows that a hand warmer purchased by campers and skiers, right, consists of sealed outlet plastic bag and an inner perforated plastic bag containing powder iron, water, salt, and sawdust. So this thing is in the cold countries where it is iced, people go out for to the mountain, to the iced thing for camping, for skiing, all those things, or for any other purposes. So because our hand and face is outer side, we cannot cover all the time. We need to have some this type of what do you call it, plastic bags. So put our hands sometimes and make it warm, and then can use my hands again. And since it is very cold there, -0, negative temperature, this type of things, the bag, it gives us some heat, but how does it give some heat? It's not a power bank, right? It is not a power bank. It is giving us heat in some chemical ways. Not yet, but probably power bank can also be used the way it is running. The engineering is running or progressing in that way that it is, I mean, what do you call it? The science fiction is very true nowadays. So now it is still in practice. Okay, this type of bags, warming bag, is still in practice. So these are used. So in that bag there is some iron powder, there are water inside, not too much, small amount, salt, and sawdust. Sawdust, do you know what is sawdust? Anybody? Does anybody know what is sawdust? I cannot see your chat box. You have to talk. I can see your chat box now. So do you know what is a sawdust? Anybody? Sawdust are, I mean, if you ever seen, what does it call? I don't know the name. That the factory where they cut or chop the trees, or logging factory, right? The things that I mean, big logs they cut in the factory. What does it call? Logging factory, probably. So in there, if you go there and then you see that when the cut the trunk of the tree, big tree, there is a lot of dust comes out from the tree, that the wood. So it is a powdered wood in that. That's why it's called sawdust. It's powder wood actually. So in that, sawdust also is there. So when this bag is shaken, and once the reaction starts actually, and then it's quite hot, it gives a lot of heat. You see that 823 kilojoule of heat it produces. So as a chemistry student, what we look is that, okay, the reaction is occurring between iron and oxygen, right? Iron and oxygen. Oxygen is a gas. Oxygen is a gas, so you have to provide enough pathway for the gas. Where do we get the oxygen? Do we bring the oxygen from a cylinder? No, we don't, because is the perforated, inner perforated. There is a perforated bag. That means we just need to open it, and then if it is when the air, the ambient air comes in close to them, the air got oxygen, so it will become hot. In the reaction will start. So as a chemistry student, we see like okay, iron and oxygen is doing the reaction, so producing ferric oxide, and then okay, so iron 3 oxide here, right? So this is producing, and then what is actually happening here, that 4 moles of iron is reacting with 3 moles of oxygen. So this is also important. 4 moles of iron reacting with 3 moles of oxygen, producing 2 moles of iron oxide, ferric oxide, right? Now it is questioning, the bag contains 15 gram of iron that reacts completely. 15 gram of iron. That iron is a very powdered iron. Actually, it's a nice and powdered iron, very fine powdered iron. Okay, so what you do is draw and label a diagram to show the energy changes that occur during the course of the reaction. Calculate the energy released by this hand warmer, and then suggest why salt is included in the contents of the bag. So this is the energy diagram. We started from here, and then since it is producing heat, so it is exothermic reaction, of course, because it is negative. It is negative, del H is negative, so it is exothermic reaction. And also the final product enthalpy is much lower than the reactants one, right? So this is exothermic. If it were like this, where the product is higher, the enthalpy of the product is higher than the reactant, it will be endothermic. In this case, it will be endothermic, but it is not the case, right? It is not the case. It is not endothermic, it is exothermic. Okay, so this is how we should draw. And if it is in the exam, you should be able to draw it nicely and then clearly show what are the things, which part of the, this, what do you call it, graph is what? That is, the reactants are here before they become mixed, and here they started, I mean, when they are mixed, they started to do the reaction. This is the activation energy, EA. We have to show it. It is not shown, but here it is shown actually. EA, this part, and from this part to this part, it is changes in enthalpy, del H. Changes in enthalpy. So question number 2 says that calculate how much energy it will produce. So here we see that 15 gram number of moles. Of course, we have to find. I said before, I mean at the beginning, what is we are looking at the reaction. When we look at the reaction, we see the 4 moles of iron is 3 moles reacting with 3 moles of oxygen to produce 2 moles of ferric oxide, and then the energy is produces 823 kilojoule per mole. Okay, 1 mole of this reaction will produce 823 kilojoule. But the thing is, I have only 15 gram. I don't have even 1 mole. So how many moles do I have of iron? So from there, it's easily find 0.2686 mole of iron, right? So stoichiometric ratio, from there we find it is 4:2, and then 4 moles produces 823, and then 0.28 moles of iron will produce how much? So it's simple calculation. We find it is 55.3 kilojoule of heat will be produced. So in exam, actually, you should write that 55.3 kilojoule of heat will be produced from this 15 gram, will be produced from 15 gram of iron. 15 gram of iron. So this is the, I mean, complete way of showing or understanding that a student understood the problem. And the salt, the question number 3 says that why the salt should be used, because it is a redox reaction, that means oxidation and reduction reaction, right? And this oxidation and reduction reaction needs some conductor where the electron will pass through. From where the electron will pass through, we need to know that one. So if we add salt, because we know that salt is electrolyte. So electrolyte means it transfer or it carries, it actually transfers the electron and faster way, so and easily, so that the reaction will be faster, and the heat will be uniformly produced from all over, rather than just mixing with one part of this. And the sawdust was produced as a base or a matrix, you can say that. So the sawdust, the iron was mixed inside the sawdust, so that 15 gram of iron is not much, right? If we have to have a big bag, a big bag that I can put my two hands together. I have to spread that 15 gram of iron all over the places. So how or where does it stay go to? So that sawdust actually is binding it or keeping it. 15 gram of iron. Second thing is the reaction is fast. The reaction occurs first, and then after it becomes hot, and then it becomes cold very fast. So sawdust will prevent it to get colder faster. All right. So it will also, as an insulator material, it will be worked, and then it will keep as the absorber. Question number 3 says that octane is a major component. This is what I was talking. Octane, just consider methane as well. CH4, methane. Or ethane, C2H6. Ethane or ethane. All right. So octane in our home cooking, we use LPG, right? Liquid petroleum gas, which is a mixture of methane, ethane, and then propane, quite much of this. All these things are natural gas, LNG, right? Natural liquefied gas, which has more of the methane inside it. So this thing actually, reacts octane that we use in our car for petrol, our fuel, car fuel that we use. Is a major component of petrol, but when you call petrol is a mixture of many things. Octane is one of them, right? So nowadays in Malaysia, actually we have 97 and 95. 95 is petrol that we call, which is a mixture of many things. Octane, 97%, which is much more purified and more of this octane there, right? So it has much more heat content. That means enthalpy produces much more heat per mole than petrol, and that's why it's expensive. But not every car needs this. Only certain car those needs higher power, maybe they need it. Okay, so this octane combustion occurs in this way. So 1 mole of octane is reacting with 12.5 moles of oxygen. Can you imagine? Can you imagine? 12.5 moles of oxygen. Can anybody give me an idea of 12.5 moles of oxygen means how many grams of oxygen? Can anybody give me an idea?
$400
Sorry, Eric?
400 gram.
400 gram. Oh, serious? 400 gram of oxygen, and then this 400 gram of oxygen, if we consider the the condition, atmospheric condition, how many milliliter or liter or something like that it would be. So 1 mole of octane is burning 400 gram of oxygen at one go to produce this many kilojoule per mole of heat to move our car how many miles? It's not even 1 mile or 1 kilometer. How much? And then we are also producing carbon dioxide. So double fold our we are what do you call it? Harming our environment. Anyway, so this is not our topic of our discussion. Maybe you will, if you learn the environmental chemistry, environmental technology, then you will learn more later on. So this octane actually is reacting with oxygen and then producing carbon dioxide and water. Water in a not a liquid form but in a vapor form. So that is why we do not see the water coming out from our engine. But this is the gas comes out. In that gas, the water vapors goes away. Okay, so calculate the energy released when 1.8 liters of petrol undergoes combustion. Given the density of the octane is 0.703 gram. So our octane density is 0.7 gram, and then it has a 1.8 liter means how many grams, because we have to know the number of moles. From only then we will find the number of moles after we convert it to gram. So 1.8 liter means 1,800 milliliter, right? So from there it is the density is 1.265 times 10 power 3 gram of octane, and the octane has molecular weight. Carbon, there are 8 carbons, so 12.01 times 8 plus hydrogen is 1.0018 actually times 18. So altogether we will see it is 114.23 number of moles. Okay, so from there we see this 11.08 number of moles, and the energy it will release is 5.6 times 10 power 4th of kilojoule per mole of energy. Kilojoule actually, not mole. Kilojoule of energy it will be produced from here, because the mole and mole are cancelled out. So 1.8 liter of octane will produce this much of energy. 1.8 liter means how many miles does it move? Depends on the car, I know, but let's say that on an average the car gives 12 mileage inside, or 15 mileage, 15 kilometer times 1.8 is 27 kilometer. It will run, right? 27 kilometer it will run, and then so how many moles did we have? 11.08. So 11.08 moles will have how many moles of oxygen burnt? Times 12.5, 138.5 moles of oxygen will be burnt, which is 32 times 4,432 gram of oxygen will be 4.5 kilo of oxygen will be burnt. Pure oxygen will be burnt. And also, you know, 11 times 8, 88 times moles of carbon dioxide is produced, which is even more because I have to multiply by 44. Carbon dioxide molecular weight 44, right? So 44 times 88 is that much gram of carbon dioxide. So just to travel 27 kilometer, how much of oxygen and carbon dioxide we are burning and producing, relatively. So does it mean that, Dr. Bazul is telling us not to drive? No, I'm not telling you not to drive. I'm saying that we need to always consider that how much harm we are causing to the environment and the ways that we can reduce or remove the bad or remove or reduce the harm that we are doing. By how? Probably we can use, plant more trees, right? Awareness, produce the awareness. What is the purpose or what is the need for the jungle that we should have, right? or 25% jungle should we have, 30% jungle should we have. Not any crops is certain type is jungle. So in jungle there are different type of plants, they absorb different type of the rate of carbon dioxide. Okay, and also reduce the pollution because the recent studies shows that the algae in the sea, it absorb 8 times more carbon dioxide than our plants do. So if we do the water pollution, those algae are dying, and then no carbon dioxide is being reduced. Okay, so it's too much talk about environmental chemistry, right? Let's come back to our thermochemistry. So, those are the things that I just wanted to share with you. So probably you will think, and then if you go for chemical engineering or environmental technology, environmental sciences, so you will learn more about it. Activation energies. Why gasoline petrol fuel tank of car does not combust spontaneously but need an ignition spark? The same thing that if we, this question actually is the same, that is asking that why do you turn on your stove at home and the gas comes out like that, but no no fire. No fire means no heat, only the gas. We can smell the gas, and that is dangerous, we know, right? If you smell gas, don't strike a match, or don't don't strike the lighter. It's dangerous. We know, everyone knows that. But the question is, why so much of the gas is there but no fire? What is the problem happening? So we'll see in the next slide with the graphic. And the second thing is that in order to initiate combustion reaction, bonds between atoms in octane needs to be broken first, of course, so that there will be new bond. If there is already one bond, how to make another bond, right? And the activation energy is the energy that's required to break the bonds to react, to produce the reactants. So now this is the octane. This is an organic molecule. And what does organic molecule means? We'll see later. After week 10, when we study organic chemistry. But just now, for the timing, it says that in organic reactant, the reactant, that is octane. Okay, so when it has to make a bond with this oxygen to somehow, because there is oxygen, but oxygen is double bonded to one another. This bond has to be broken, and also their bond, this hydrogen bond, has to be broken with carbon. Only then this hydrogen and oxygen, they will produce the bonding, right? So what is happening here? Oxygen is here, oxygen is here, and these all compounds are here, right? They're here, and they're moving around, all around, to each other, occasionally bumping to each other, and then they're not doing anything because they do not have that much necessary energy to break the bond, which is here. If they are here, they are just oxygen. If they are here, they are just the O2. But when they reaches here, the energy, actually, the time passing by, this is the same thing happening, that when you turn on the gas stove but no match, the gas is coming out. The gas and oxygen, the air, got oxygen, they are always in your kitchen as well. It is bumping each other. We can smell the gas. That means the gas is there, but there is no fire, because there is not enough energy to overcome this barrier. Probably they are here, they have this much energy, probably they have this much energy, but they do not have this much energy. This much energy can be given just with a slight strike of the match. Okay, what does the match do? The match, when we strike, that means a spark goes on, and the spark one spark, it is producing a heat, a small amount of heat, but heat, right? Small amount of heat, but heat. And that heat is taken by one, let's say one molecule of this gas and oxygen. And then they produce a bond. By this producing a bond, they themselves release some energy, and that energy is taken by the another molecule. That energy is taken by another. So that is how boom, the gas starts to fire, burn, right? So this is the gas actually, I mean, the match strike gives us the activation energy here. And once they start to form the bond they make is much more stable than the gas or oxygen themselves, right? So the product carbon dioxide, and that is why, okay, this is another thing that I'm going to tell you about the environmental chemistry. Okay, so that is why the energy will start to drop. Energy will start to drop because they have much more stability. Carbon dioxide that is produced, it has much more stability. That is why it is not that easy to remove carbon dioxide from the environment. Once it is produced, it is very hard to remove. But those plants, algae, the ocean, they are doing it so easily and just free for us, right? So we have to be aware, and we shouldn't allow anyone and everyone to chop down the trees or the jungle for developing something unnecessary. Okay, so this is the activation energy, and this is the enthalpy of the heat of the product. And now, since we are talking about that they are here, they are bumping to each other, from this we can understand the collision theory. All right, so that means they are bumping together, they are having a collision together. And yes, they are having collision together. They're always good having the collision, but some collision, when they are having much faster collision, right? They have much faster collision. What will happen is they will eventually overcome that barrier. So the same thing can occur if I do not, for this gas, right? For this gas, when they are bumping to each other, I said they are bumping each other, but there is no fire. But imagine that the same gas that we use for the natural gas, the petroleum gas that you use for cooking, we put it in a container, in a jar, or in a can. It's a metal can. Let's say it's a metal can. We put it in a can, and then there is no strike in that can. Quite much of the gas is there, but what we do is there is no match strike there inside the can, but we put the can on fire. What will happen? The heat will be absorbed by these free atoms, and then they will start to collide much more faster because of this heat. The heat is giving them energy to collide more faster. They are colliding, and eventually they will go up this barrier. And that is why when we see the cylinder, right? The gas cylinder, when we put it on the fire, on the flame, it explodes. Even though inside cylinder there is no spark, but the gas, the temperature has given them enough energy for the free molecule, free atoms to collide in much more greater energy, so that they will eventually overcome that the activation energy, and then they do the reaction. I hope that you understand what I'm trying to say. If not, please respond so that I can say more. Okay. All right. So here question number 4 says that which of the following graphs most likely to represent the slowest forward reaction? Slowest forward reaction. That means this is the reaction progress is going that way, right? And the energy is here, the going up. So if we start from here and then this energy is so high, that is 150 probably, 150 or 125, something like that. And for B, it is 100. For C, it is like 150 as well. For D, it is like just like 70, 75 something. Oh, it's given, yeah, 25. And then 50, 100, 20, 75. So these are the energy, activation energy. Since the activation energy for A is much higher, it will be much slower, this reaction. That means the reaction, it will go to this part, but it will go very slow. It could go very slow because it had the bigger mountain it has to overcome than others. 150 and yeah, so it is 100. Oh, we started from here, right? So yeah, 100 is 75. So it has a bigger inner mountain to cross over to get to this product, so that A is the most slowest. Another one is which of them are exothermic? Which of them are exothermic reaction? Can anybody tell me which of them are exothermic reaction for here? A, B, C, D. Which of them are exothermic and which of them are endothermic? So A and B is endothermic or exothermic?
Endo.
Yep, good, thank you. So A and B are endothermic because the product, it is the product, right? This is the reactant side. This is product side. So the product enthalpy is higher than the reactant. So this is endothermic. But for this, product is lower than the reactant. So this is exothermic. That means they are producing heat. They are giving us more heat. They are exiting heat, right? So these two are the exothermic. Now, how do we make the reaction go faster? Before we go there, please go to menti.com, and then put this and use the code, this one. So 61641663. So please put this code and then put your answer there, right? And then we'll, after that, we'll go there to see so I hope that you can see and put your answer in a few minutes. 2 minutes. I go make some tea for myself.
Sir. Sir. Oh no. Voting is closed.
Oh, voting is. How do I? Oh my God. Oh, it's so easy, but I was looking. Okay, so once again, please try now. Voting is open now. The 4 votes I got, another 2. Other students just left. Okay, so looks like it's going to be a tie. All right, so forming new bonding in different molecules seems favorable, right? And that is why they will produce the reaction, new bonds. So the high temperature, it's not necessarily that high temperature will always force them to form the new bond. Sometimes high temperature may even force them to break rather than producing a new reaction to break down. So not always the high temperature, it is mostly the new bonds they are producing, it is more favorable, or you can say in another way that it is the energy, the product, the energy of the product that will be produced by having the new bond, it is much more lower or more stable than in the reactant. Okay, so again, we go back to our lecture, and then the reaction, how do we produce the reaction to go faster? How do you produce the reaction to go faster? If we want to go, make our reaction go faster, we have to understand what are the things that produces a reaction. What are the things that the reaction depends on, right? What are the things that reaction depends on? The surface area. The reaction depends on the surface area of what? Of the reactants. The reactant surface area. Probably it will be a little bit something that you need to consider. What is the reactant surface area? I'll explain it. And then increased concentrations of reactant. Concentration, if it is increases, pressure of gases, right? But there is something that we should also consider. Increase the temperature. I always say that temperature, yeah, mostly it will increase. It will increase the reaction rate, or when the temperature is hot, we ourselves also feel like we're not stable, right? We become always feisty or not in good mood if the temperature is so hot. So that is the same thing that molecules will also not feel very stable in the high temperature. And then catalyst, using catalyst for one for a reaction. That is the way we can increase the temperature, reaction rate. So surface area. Surface area is, I'm not sure whether you already know about this term, but the surface area, right? So this is a ball. The surface of the ball, the periphery, a ball is what does it call actually? This is circle. This is circle, and the ball is a 3D circle. What does it call? I forgot.
A sphere.
Sphere, yes, thank you. Once again, Vanessa, thank you. So the sphere, we know the surface of the sphere, right? So if I have this big sphere, right, and I have this big small sphere, let's say that I have 10 of these. I have 10 of these. So this is category A, this is B. Which one do you think will have bigger surface at the surface? A or B?
The smaller one.
Yeah, okay. So you are that means we know about the surface area, right? So if we break this big ball or sphere, we will get many big smaller balls or smaller particles that will have higher surface. So if we increase the surface area, why it will have more reaction? Because it can heat, or no, not this way, sorry. It can increase the collision between them. So they will have more collision. If there is only one ball, there is nothing to heat with. But if there are 10, I break one and make 10, so they will have 10 times, or at least 8 times there is a chance that they will collide to each other, right? Or more than that actually. So if we have the more smaller surface area, there is a chance that they will have more frequent collision. and that the collision, frequent collision means there is more possibility that there will have more reaction. Examples are sherbet. I don't know whether it's, I mean, kids nowadays still do this, but usually that was malic acid and sodium bicarbonate. You just need to open it and then put on your tongue. It will become fizz, and then some, with some smell, it produces some. And because of this sodium bicarbonate, the carbon dioxide produces, and it the carbon dioxide, this bubble produces on our tongue, and it feels good. Another example is the firecrackers. So in that firecracker, actually, we need to, the aluminium and the gunpowder, it has to be mixed well, and how I got it, the better mixing or the finest particle they have in both cases for aluminium and also for that gunpowder, the better mix it will be, and then they will have faster, more speedy reaction, because they mix together nicely. If we do not mix, the aluminium is coarse, so it will not burn that much. So for this type of firecrackers, when the firecracker needs to be burned very very fast pace, it will be smaller or very fine particles, and when it needs to be low burning thing or burning fuse, it will be bigger particles of these things. Concentration of the solution. Concentration increases. Concentration means there are more particles we are putting, so that we are actually giving more option for it to collide each other. But the thing is, if it is true for gaseous particles, right? It's true in gaseous particle, but if it is a solid, or sorry, it is a liquid thing, too much concentration will also sometimes inhibit the reaction. If it is too much concentration, that's why for a liquid phase or liquid state, right, we need to produce some low concentration one from the higher concentration one, because higher concentration in liquid. But this is true for a gaseous phase. When it is gas, the more concentration means the pressure increases. In a beaker or in a can, you put more gas. That means you're increasing the concentration or increasing the number of particles inside. Temperature means you're producing or you're providing more energy to the particles. All right, more energy to the particles, and that is why with the more energy they start to do more hooding together, the colliding together, collision together, and then they will have more chances to produce more faster reaction. So now this Maxwell-Boltzmann distribution, actually, it is just a simple way of introducing you to the Maxwell-Boltzmann distribution curve. Is not this simple thing, but if using this Maxwell-Boltzmann, we can see that higher temperature, all right, higher temperature, the number of particles, they do not, the kinetic energy, actually, the kinetic energy is increasing for less number of particles, but for the higher number of particles, but the less number of particles at a time, the kinetic energy is increasing for the more number of particles at higher temperature. So this is under 30 degrees centigrade, and under this curve, anything is the number of particles. All right, the portion of the particles that is under this temperature, under this. So when we increase the temperature, the kinetic energy of potential energy of this element or molecules, it is translated to this kinetic energy because it is increasing towards more particles will have the higher energy than in 20 degrees centigrade or low amount of temperature. And that is why this explains that why in higher temperature more reaction occurs, frequently reaction occurs. So we see that this is 30 degrees 20 degrees centigrade, and the particle under this 20 degrees centigrade is this much, right? There are at 20 degrees centigrade the reaction is still occurring if this is the activation energy, right? If this activation energy at 20 degrees centigrade the reaction is occurring, but not that much. But at 30 degrees centigrade we see more particles are inside. More particles are inside, so more reaction is occurring more vigorously, more fast, speedy. Okay, so here it says that use the distribution curve to account for the increase in the reaction rate with increasing temperature. So it was just now I was describing why at 30 degrees more will have higher energy or do more reaction. Catalyst. What is a catalyst? Does anybody has any idea of what is a catalyst? Anybody? A catalyst is a material or a chemical sometimes that produces or provides an alternative pathway to lower activation energy, to lower the activation energy. The activation energy, the curve that we have seen, right? The curve that we have seen, if we could lower it, that the molecules does not have to go through these higher hills, it goes through this much so that more particles can do the reaction and can go faster. Exactly the same thing the catalyst does. So it reduces the pathway or the activation energy. And there's in many different type of production, there are different type of catalysts are used. Mostly here we are showing the metal catalyst. Metal catalyst means titanium, aluminium, iron, vanadium, zeolite, nickel, or solid or metal catalyst we are showing. But sometimes the catalyst can be liquid as well. All right, can be liquid as well, or semi-solid can be as well, that we will be using for as a catalyst. So homogeneous, there are two ways or two different categories we can produce, that we can divide categories. Catalyst. This is homogeneous. The catalyst is also at the same state with the reactant and product. And heterogeneous, which is not at the same state. So here for polyethylene, right, we are producing polyethylene and we are adding ethane, which is a gas, and polyethylene is a solid, right, the plastic, that is the plastic. And we are using titanium. Titanium is a metal, or aluminium is a metal. So it is not a homogeneous because it is not same with the product or the reactant. Same goes for ammonia. We are adding nitrogen and hydrogen to produce ammonia, but we are using iron. So iron is solid, but ammonia is a gas, nitrogen and hydrogen also gas. So it is not same state or same phase as in the reactant and product. So this is heterogeneous catalyst, right? How do the catalyst work actually? The catalyst, when let's say for the ammonia process, Haber process, this is a revolutionary invention actually. Because of this, there are so many things happens. I think we will discuss later. So many things happen. Even in it was used. This was the most important invention during the First World War, and also for our food security. So probably I'll talk more. So this Haber process, right? And during the Haber process, nitrogen and hydrogen, they are coming together and they're sitting on this iron. Let's say the iron, the surface, they are giving a good cushion for nitrogen and hydrogen to sit together. Because nitrogen and hydrogen, they are always, they both are gas, they are always here and there, they are going there and here, and then they're occasionally having a collision, but then they are going away. They are not coming close, that close. But when we put some iron, fine, of course, iron powder. So this iron will, nitrogen and hydrogen will come together and sit together on that iron, and then they will have the reaction. And this is not that simple, and this, still we are trying to understand how the catalyst actually works. So this is a catalyst actually. I mean, this is a very broadly or grossly, it says that the catalyst, how this work. And when it works, the catalyst, without catalyst, the energy is this high, the energy barrier. But when we use the catalyst, the energy barrier is so low. And this is the activation. So we need to produce, give a little bit of, if it was 150, let's say, 150, it is 100. So we have to provide 50 kilojoule less to get that reaction done. Catalyst is revolutionary in that way. All right. So catalyst, when we add in the Maxwell-Boltzmann distribution, also you can see that after it goes through all those things, it has only this amount of molecules under this curve. That means it has qualified for this kinetic energy. But when we add catalyst, much more of this number of particles actually goes under this distribution or under this kinetic energy. Okay, so question number 6 says, which energy values will change when a catalyst is added? All right. Only C 2 and 3, if we use the catalyst, only the activation energy will be changed, and the reverse reaction, when the product goes to form the reactant as well, that energy will also change, but the enthalpy will not change. Whatever the product was supposed to be produced from that reactant, it will always be the same, doesn't matter you use the catalyst or not. Okay, if you use the catalyst, yes, the product will be produced much easier, but it's still the same product it will produce. So enthalpy will never be changed. So as a summary, if the product is here less energy than the reactant is exothermic, and if it is higher energy than the reactant is the endothermic reactant. All right. So this is it for today. And do you have any question, anybody? No. So actually I have another. I have another Menti question. Please go to the menti.com again and use this. Use this. What is that? Okay. It's quite easy. Please take the quiz and vote it. I don't have much time. I will set the time to 1 minute. So in 1 minute, you have to yeah, 1 minute you have to vote. Oh, good. All right, 3256. Okay. Anybody wants to? Is there anyone else there? How come? I can only see 1, 2, 3, 4, 5 of you are here, but many of you are voting. From where you are coming? I cannot see you guys. One, two, three, four, 5 is here. I should see, but there are 9 votes. Okay, so yes, many of you actually got it correct. Almost everyone got corrected because these two are both of these. There are higher temperature and there is lower energy hurdle. These two are much more correct, then there are more reactant. There are more reactant means not always, right? Not always, but higher temperature always favors, mostly it will favor the reaction to occur. Either it is breaking or it's forming, but it's doing. And of course, if the energy barrier is low, the more reactant will go to the product side. Okay, so thank you for voting, and yeah, that is it for today. I'll see you next Thursday during the lab, our thermochemistry lab. Okay, so please submit your lab before that report. And of course, on Friday, I'll see you for the tutorial. And next week is the big week for our midterm test. So yeah. Any question anybody has? Anything? No? All right, then all the best. See you. Take care. Bye-bye.